So functions in general just take a value, it does something to it, and it gives me an output. Okay, so for these three, sine, cosine, tangent, and there are a few others, what they take in as an input are angles. Okay, so they're going to take, let's say, sine. Usually it's abbreviated with SIN, sine. Okay, you'll take sine of theta, where theta is an angle. So now I'm not just taking a number, I'm taking in an angle. That angle is usually measured in degrees, which, you write as like 45 degrees, like that, right? And, which you've probably seen when people say like 360 degrees, right, as a full circle, or radians. And I think I'll probably make a video on how to convert between degrees and radians, but usually you'll see something like, 2 pi over 3 radians, or even just a decimal, okay? And the pi is just because you're moving around a circle, and you have to do something with the circumference and stuff like that, but you don't have to worry about it. These are usually the units for angles, and this is theta, which is a common variable to stand for angles. But these take angles and they output a number which is actually a ratio. It's actually a ratio, which we'll get into. So, basically, how do we find what that number is and what ratio exactly? Well, that's what we're going to do with our right triangle. So, trigonometry is all about studying triangles. Trigonometry. The foundation of trigonometry is actually just all about trigonometry. It's almost like going from geometry to trigonometry, studying triangles. Okay, so here I have drawn a right triangle, which means that there is one right angle. That right angle means that it's 90 degrees. It's right. Or in other words, this side is perpendicular to this side. Okay. So not all triangles are right. I mean, I'm always right, but whatever. Not all triangles are. Just kidding. Okay, so like this is not a right triangle, because notice it is a triangle. It has 3 sides, 1, 2, and 3. But 1, 2, and 3 angles, right? But none of them are perpendicular, none of them are right. So we can find some properties of non-right triangles, but really we derive all those properties from the use of right triangles. Like I might draw something like this and get 2 right triangles here, for instance. So properties that we get with non-right triangles really rely on the use of right triangles. the side that is across from that right angle right here is the longest angle, longest side, the longest side, and that is called the hypotenuse. Okay, hypotenuse. This is the longest side compared to this and this. We can kind of visually show ourselves that, but oops, let's measure from yeah, this is not really okay, let's do it this way. This is like almost 5. This is not, it's like 3.5-ish. And that is almost a 6. Okay, so you see that? So this is definitely the longest. And we actually know how the sides are related in a right triangle. If you recall, let's label the other two sides that are not the hypotenuse A and B. And it doesn't matter which two, like which is A and which is B. Let's label the hypotenuse as C. We know that A squared plus B squared equals C squared because of Pythagorean theorem. Which tells us if we have a right triangle, the sides are related in this way. And it also tells us that if we have a triangle where the sides are related in this way, the triangle must be right, which is an often forgotten piece of the Pythagorean theorem. But my point being that we already know how to relate the lengths of the sides of a right triangle. And that's all cool and fun and dandy, and there's actually a fun proof of this. But now, for trigonometry, we also can relate the angles of the right triangle to the sides, which just totally blows my mind. We can relate an angle to a length or a ratio. It is actually a ratio, but we'll see what that means. So we're going to have these functions, sine, cosine, tangent, and from them we can opposite from it, which is the one that's across. Okay. This is the side that's opposite from theta. So I could just do something like this. OPP, opposite. Okay. And then notice that there is a side that is touching this theta. That is not the hypotenuse. So this side is adjacent, but that's the hypotenuse. So this is the adjacent, that's the ADJ, adjacent. So this is the one that's like touching theta, but isn't the hypotenuse. And then this is the hypotenuse, right? Hypotenuse. So that's gonna be our, like this is ADJ, that is opposite, and this is going to be our hypotenuse. Okay, so now you can kind of see what's happening. We're going to use these to find the sine, cosine, and tangent of our angle. So what that means is, for this angle theta, so you have to actually be clear which angle you're talking about, okay? So we're going to do theta, this theta. So what the SohCahToa means is that we have sine theta equals opposite over hypotenuse. So we have to remember that it's actually a ratio. So this opposite hypotenuse is opposite over hypotenuse. So that means that for this angle theta, we take this side, the length of the side that is opposite, which is A, over the hypotenuse, which is C. So sine theta here is A over C. Now remember, in a lot of problems, you will know or be able to calculate the lengths of these sides, okay? You'll either be given this, or you might apply this in like physics problems or something, but you will be able to figure out two sides that are perpendicular. Now you might not be given the hypotenuse, but you can calculate it, remember, using the Pythagorean theorem. But in either case, you know that this ratio is true. So A and C and B are just placeholders for now for lengths of sides, okay? But you can see now, in theory, you could see how you take an angle, and this trigonometric function tells me that A over C, these are both lengths of sides of the triangle. When you divide that, it becomes a ratio. So you might get a number like 0.15, I don't know, 86 or something like that, okay? That's what this means. That's what the number actually means. So you'll have to adjust that per your problem, but I'm sure we'll do this in the future too. And we'll also use this concept for inverse trig functions. But that's the setup. So you can apply this pattern for cosine and tangent. So actually there's a secret like divide between each of these. But you know, like opposite over adjacent, or opposite over hypotenuse, or adjacent over hypotenuse. Now, if you've already learned about tangent before, you'll know that tangent is sine over cosine. So technically, this is redundant, because if we know something is opposite over hypotenuse divided by adjacent over hypotenuse, if we just multiply the top and the bottom by h, we get opposite over actually need that, but it's nice and pretty and it's easier to remember, and we don't want to have to do this every single time. So that's why. Okay. Okay. So really, let's try the same thing with theta, but with cosine. So we see ka. So adjacent cosine is adjacent over hypotenuse. So we're gonna do cosine, which is abbreviated as cos theta, is adjacent. So the side that is not the hypotenuse, but that is touching theta. Okay, adjacent over hypotenuse. So now I'm going to start abbreviating as ADJ over hypotenuse. So that will be B over C. That's it. Good job. It's not too bad, right? It's not too bad. I think what's confusing is to know which side is opposite, which is hypotenuse, which is adjacent, if you don't take the time to understand that in the first place. But it's kind of cool, right? Because you're getting ratios of lengths of sides. So, finishing that off, we can do tan of theta, tangent of theta. Tan is, so then we have toa, so opposite over adjacent. So opposite from theta is A, and opposite over, or adjacent from theta is B. Okay, so I should have written that that's opposite over adjacent. A over B. It's pretty cool, right? Okay, so you can actually do this whole thing with a different angle, like this one. Alpha, let's see here. Let's see. Okay, so let's say this is alpha. Okay, usually we use Greek letters for angles here. So notice that if we used this as our angle and we tried to find like sine of alpha or cosine of alpha, in fact you could try this on your own if you're interested and if you're not already asleep. Basically, you would have to relabel which ones are adjacent and which sides are opposite. The hypotenuse is still the hypotenuse, which is why you only usually really do this with theta and alpha, like these two other angles. You don't do this with the right angle here, okay? Although there are special properties for sine and cosine of 90. But when we talk about SohCahToa, we're talking about one of these two angles. So remember though, that if we're working with this angle, the opposite is actually this side now, so this is going to get kind of crazy here, but this is opposite, and then this side, remember, it's the side that is touching the angle alpha that is not the hypotenuse, so this will be the adjacent side. So your ratios will actually be slightly different. For instance, sine theta was A over C, but sine alpha will be B over C. So take your time with this when you first start out. Just get a sense of what opposite is, what adjacent is, which one's the hypotenuse, and then get used to using the SohCahToa as a mnemonic. But then from there in the future, it will get much easier. Like you won't even need to write opposite over hypotenuse anymore. You can just know, like, okay, A over C or B over C or A over B. Okay. So then we can start plugging in numbers and stuff like that, which is what we will do in the future. And yeah, so that's the basics of SohCahToa. I hope that that kind of makes sense. From here, what's actually very interesting is you can actually prove one of our trig identities that says sine squared of an angle theta plus cosine squared theta is 1. And this is a neat little algebra thing that we can do, I guess, later, but you can plug in a over c and b over c here and use the Pythagorean theorem to show that it's actually 1, which I think is cool. But the use of SohCahToa is actually, we can have direct problems like this, like finding the angle or finding what sine of theta is based on the lengths of two sides. But we also use SohCahToa, like I said, in physics problems or even on the unit circle. So the idea of the unit circle is that we will have this horizontal be the x, so the unit circle is on the coordinate plane, and the hypotenuse is always going to be 1 because it's a unit circle. It's a circle that's centered on the origin and has a radius of 1. So you'll see this triangle a lot. Because the xy coordinate plane, the x and y axes are perpendicular. So we have this as the right triangle. So if you can imagine that as our angle, this is our angle, we can do opposite hypotenuse and adjacent and stuff like that, where hypotenuse is 1. So you can do a lot of really cool stuff with that. So I hope that this was